In the linear inequalities introduction video, we learned we can represent all points that make an inequality true by graphing a line and shading the section of the graph where all the correct answers are. Before we dive in deeper though, let's revisit what we learned about solving inequalities earlier in the course. If you remember, the normal less than and greater than symbols were represented in two ways on a number line. Since these symbols do not have the equal to underline, we use an open point on the number line to visually show the number at this point is not included in the solution set. Then, the inequality symbol also controls which direction we shade on the number line. Less than symbols require us to shade left because that's where all the points smaller than the boundary point are. And greater than symbols require us to shade right because that's where all the points bigger than the boundary point are. Finally, we learned less than or equal and greater than or equal symbols have the same shading rules, but the only difference is we used a closed point for the boundary point. The closed point visually shows we do want to include the number in the solution set. With this in mind, here are 4 linear inequality examples. The first step in graphing a linear inequality is to graph the boundary line. This can be done by using what we learned about graphing linear equations in the last chapter. We know from slope-intercept form, -3 is the y-intercept and 2 is the slope in each of these statements. Therefore, we can use that information to graph our boundary line. Now, this is where the inequality symbols kick in. Before, when we graphed on a number line, the normal less than and greater than symbols required an open point to show we do not want to include the boundary number in our solution. Now we need to do something similar with our boundary line. Instead of an open point, we use an open line, which is represented as a dashed line. Similarly, the less than or equal and greater than or equal symbols were represented by closed points on number lines, and now our closed point is a closed, solid line for the boundary line. Again, this means we do want to include the points on this line in the solution set. Finally, the inequality symbols also tell us where we need to shade. Again, on the number line, both types of less than symbols required us to shade left where the smaller numbers are. Now on a graph, we still want to shade where the smaller numbers are, and that happens to be down or below the boundary line. And as you may have guessed, greater than symbols require us to shade up or above the boundary line where the bigger numbers are, just like how we shade it right on the number line where bigger numbers are. That's pretty much it for graphing linear inequalities. Use what you know from linear equations to graph the boundary line, and then use the inequality symbol to determine whether to draw a dashed or solid line and which direction to shade. However, there is one more thing to look out for. We sometimes need to reverse the inequality symbol just like we did when solving inequalities. Here's a standard form inequality. 3x minus 4y is less than 12. Let's quickly convert this to slope-intercept form to show where the reversing happens. We can begin by subtracting 3x from both sides to get our mx in the correct location for y equals mx plus b. Then we can divide by -4 on both sides of the equation. Stop right there though. If you remember from solving inequalities, anytime we multiply or divide by a negative number, we always have to reverse the inequality symbol. Therefore, our final answer for this inequality is y is greater than 3/4 x minus 3 instead of less than. Watch out for situations where you need to reverse the inequality symbol because it changes the direction we need to shade on the graph.